I'm Mira.
And I'm Chris. We are associated members of ML4Q.
And you are listening to ML4 Q&A, a show where members from the Matter and Light for Quantum Computing cluster talk about their careers, their research, and the future of quantum.
Before we begin this episode, we have two exciting announcements. We have expanded the podcast team. The episodes with the new hosts will be out soon. And now our listeners can also catch us on YouTube.
Maybe this is also a good point to say thank you to some behind-the-scene people without whom the podcast would not work. Alexander Yan is responsible for post-production and design, and Marianne Barsum has produced most episodes up to now, a role recently taken over by H.M. Uludal.
Today, we are excited to welcome Michaela Eichinger, Product Solutions Physicist at Quantum Machines and a quantum content creator. Michaela shares her perspective from both academia and industry on the rapidly evolving quantum computing field.
We dive into her journey from her PhD at the Niels Bohr Institute to her role in pioneering scalable quantum control technology in a deep tech startup. Michaela also shares insights on the recent Nobel Prize in Physics and its impact on the field.
We also explore her thoughts on bridging academic research and industry applications, the challenges of scaling quantum systems, and the growing importance of quantum science communication.
It's a dynamic conversation packed with expert insights and inspiring stories. So let's get started.
So, Michaela Eichinger, welcome to the ML4Q podcast.
Thank you so much for having me. I'm Christian and Mira. It's great to be here.
Yes. You have a PhD from Niels Bohr Institute in Copenhagen, and you are now a product solutions physicist at Quantum Machines. And we will, of course, discuss this, as well as that you are sort of now become a quantum content creator and really a quantum computing explainer, which is, a very important role. But let's start maybe with current events and discuss a bit about the Nobel Prize, which was just awarded a week ago at the time of recording. How excited are you about the 2025 Nobel Prize?
I was extremely stoked. I think I have a colleague, calling me actually, and I was not even aware that the news broke out. And I think for the entire day, I had like a little buzz because, as you know, it's John Martinez, Michel de Vauret, and it's just this testament to the field of superconducting qubits or electrical circuits and using them for quantum application, really looking back at the foundations there. And since I did my PhD in the field and I'm now, of course, a big supporter of superconducting qubits and circuits and very much always follow the news and the state of the art here, I think it just, made me very happy and very excited for our field.
Have you met any of the laureates?
So I, of course, saw talks of them in person. So John Martinez, for instance, he also was at APS this year. He hosted a lecture at our booth. From Michel, I saw a very nice talk last year at a small conference that was about scaling superconducting qubits. But so far, I've never had the chance to chat with them in person, but I hope very soon because we have another conference coming up. So for sure, I will try my chance there.
Did you notice any boost for the quantum industry and particularly for superconducting qubits after this announcement?
So boost, of course, yes, for sure. But I think overall this recognition, that this is really a very novel technology that now, is becoming more mainstream, right? It's really a testament to the foundations. It was not trivial that we can have these quantum effects on a more macroscopic scale and that you have a device that you can hold in your hand and you can literally see the circuit and that it exhibits these quantum effects. And I think this is one thing, but then, building up from that we can build useful components out of it, right? And one component is very much, of course, a quantum processor, but there were other technologies besides that were spinning out of that as well. And I think this Nobel Prize really shines the light on this novel technology. But I also want to emphasize that in the race of quantum computing and processors, there are, of course, other technologies that are just as exciting. that we all need to be aware of and to watch out for.
You're also a bit of a quantum explainer now. And I personally got a little bit annoyed because, of course, the announcement reads macroscopic quantum mechanical tunneling and energy quantization. The energy quantization is very good. But one of the problems was, of course, that there's a little bit of a focus on this tunneling aspect. I find it was maybe not exactly ideal because people got, if you looked into the general public, you had people talking about tunneling diodes and all this stuff, right?
I think that's again, it's really, deep foundational physics, quantum mechanics, and then it's often hard to bridge there the gap, what is actually the spin out effects of this? What is the novelty here and what came after? And then dissecting this and putting it into a wider context, I think is always a struggle that science has, especially if we are in this very, weird field of, quantum physics.
Yeah, it's very difficult to tell our research stories in a way that is not either misleading or very technical.
Finding the bridge, right, and being able to convey these ideas. But I think Michelle and John are actually, excellent in explaining these concepts. So I think they're also now giving lectures. I really look forward, or they're already given some lectures. I saw some snippets online. They're excellent educators and teachers, right? That's why they are professors. So I think listening to them directly helps understanding, what they did and why this was important.
And I have to say, I did if you read this Nobel press release, they had this nice sentence that was saying that the charged particles moving in the circuit behave as if they were a single particle that lives in the entire circuit. And that's, of course, that really gets closer to the right idea. While the tunneling effect, to me, it always was the problem. If you say, you have this tunneling, it's a very local effect, but
yes, you want to span, right? You want to tie it to the macroscopic nature here, right? And
also, both of them have companies, right? So it's going to be very exciting to see. It's unusual. I don't think there have been many companies that are in their cases order of 5 years old or even younger. In John Martinez's case, of course, has a startup that is just sort of came out of stealth and got a Nobel Prize. It must be pretty, I don't think this has happened many times.
Oh, it's probably an extremely super exciting time for him, right? So much happening because especially with early stage startups, right? We're working close with his company Colab, and so it's just wild times and so much movement, in the entire industry. And especially on these components, there is really a strong push and passion to solve these scaling issues that we're having. And I think it's great to see it also, tackled from multiple angles. And we see different philosophies and, foundational concepts popping up that those groups focus on.
Yeah, and it's really funny because we should talk. We will now get back to your story in physics. But it's very funny, one of the early papers now from Colab, I think maybe they are already mentioned, but it's John Martinez and many of the people who are involved. They had a paper on Josephson junction fabrication that is very similar to your PhD work in some senses, right? So
yes, I think it's trying to solve these issues that we have with nanofabrication of these circuits overall, and how to make it reproducible, right? Don't have frequency crowding at scale, and looking at newer ways of how to realize these chips or these devices. They're very established techniques and they've worked well and they brought us to a certain point. But in, the past decade, we still haven't solved for this issue that there will be a frequency spread of the qubit frequencies when you have a wafer scale fabrication, or even just on a single chip. Doing it reproducibly is a challenge. So I really like it when I see more different kinds of techniques that are not just iterations of one another pop up. And that's what I worked on as well. I mean, there was some work at, I think it was Yale, if I remember correctly. There was some stencil work, but nobody iterated on or brought it further. They did one experiment and then it was sort of like rested. So for me, it was very exciting to like jump on it and try to do it a little bit differently and see how far that goes.
But let's start a bit earlier. So you are you started out studying physics in Regensburg. How did you decide to study physics? Like what got you into this?
So it was actually, I was torn between two topics. Initially, I thought I did not study physics, but psychology. So I had my psychology spot because for that you have to apply. I think with physics and other degrees, you typically get a spot, right? It's, they just filter out then the first 2 semesters just by making the exams hard. But yeah, I was very, torn between those two, and could not really make a decision. But physics, in my view, was the harder one. And I thought, if I don't try this harder one, I never know what would have happened. And yeah, because I think when I was also in school and at the beginning of my studies, I had this picture in my head that many had in their head. It's like, okay, physics and math are super hard. It's really just not for everyone. It's especially also not for women. And so these were the pictures that I grew up with. But there was always this part of me, let's just try and see how far I get. And then I seem to have gotten very far with it. And I think in general, choosing physics just gives you a lot of, fundamental capabilities to do a lot of things afterwards. So I thought by just studying physics, I'm also not locking myself in and leaving my future open in some sense. I think that's how I got into the degree. But and then, you're exposed to various topics in a standard physics bachelor's, but somehow I was always, a bit captured by the hands-on quantum physics part. And I seem to have chosen my bachelor thesis and then master thesis as well to look at these angles a bit more in detail.
For your bachelor's, you worked on quantum dots. What drew you to this?
So I think at this point, any kind of hands-on work, even if it's like quantum dots, was like very new, right? So I'm not sure how it was at your universities, but for me, it was like, oh, who are the professors around that I like, that other students typically go to? And then where do you get a spot, right? And I think in this case, having this small bachelor, thesis on quantum dots was more like a happy accident. And I had great advisors there and really started looking more into, the Coulomb physics. And so there but it was not like a chosen thing, like, oh, I want to do a quantum dots thesis or project. It was more just that the general environment and just drew me into that. And then I think from there, I was, of course, a bit more selective in my master's. I knew I find this kind of low temperature physics, semiconductor physics interesting. And I think from there on, it drove more towards, towards also what I did in my master's, which was 2D materials and studying transport. So it was always, and that, of course, also at low temperatures. But yeah, so these were like the themes that were also present, or like the topics and PIs that were present in Regensburg, and that's how I got into this hand-on experimental work. Mm-hmm.
You also did an internship with Infineon. Mm-hmm. How was it to get early insights into the semiconductor industry, and how did that help you later transition into the superconducting industry?
Mm-hmm. So at that time, I think what I did at Infineon was very decoupled from my degree. I think it's very standard that as a master or bachelor student, you look for a student's job. And in my friend circle, there were basically 2 friends of mine at that time who worked for Infineon. And then they wrapped up, and so they had to fill in the position. And then I was the lucky one who was able to take over. And it was in a department called reverse engineering. So you literally look at competitor devices, and I had to look at SEM images, and analyze and categorize what I see and put that in a database. But at that time, I think I didn't make this link yet to what would come, right? And my interest really in circuits overall, in electrical circuits. But I learned actually during that time valuable tools that I find now very handy in my industry job coming back. And it's interesting how things often play out. You do things just, because you're a student, you're looking for a job. And then this is pretty cool because I get to, also do some different science and still look at, SEM images and learn about different kind of technology that I haven't come into touch with. But it's also these practices around it, right?
Yeah, and it's kind of cool because Infineon, I mean, I guess like your work wasn't related to quantum devices then, but to like semiconductor, or like in broadly speaking, it's a semiconductor company, right? Mm-hmm. But they have now also become a player like a major player in German quantum in quantum information and quantum computing in Germany and beyond. But they're probably one of the biggest companies in this in Germany, and yeah.
Yes, that's super exciting. So I follow also what they are doing on the fabrication side. They had a recent paper, and it's cool that they're repurposing, entire fabrication lines that they have, or production lines, and trying to make that work for superconducting qubits. But of course, they also work on ions. It's a big company. And I think you said it when I joined, I think this was like not a theme at all at that time. It was like way too early for those companies to jump on these technologies, right? It was more than 10 years ago, or around 10 years ago.
Yeah, and if I understand it, I mean, my understanding of ion traps, for example, is pretty limited, but Infineon is now a pretty major player in the making of ion traps, and like they have the capabilities, and maybe they will become like the European, I mean, certainly they have the goal of becoming a European version of like Sandia National Labs, which makes a lot of ion traps in the US.
It makes a lot of sense. And I think I like also they work with a lot of these academic groups in the European ecosystem and fabricating for them. So it's interesting whenever I see, an ion trap talk, typically their logo pops up somewhere and they are involved in commercializing and bringing these systems to scale.
Yeah, and indeed, this SEM picture you mentioned, they showed these pictures of these crossovers, microwave crossovers, right? I guess probably niobium in their case. I don't remember exactly, but it was indeed quite a beautiful picture. I mean, I've made these type of microwave crossovers on circuit QED chips during my PhD, and they were maybe not as pretty. Like it's pretty cool, and yeah, they will play an important role in this European ecosystem. Like we don't have that many players at that level in Europe. So, yeah.
And they have the tools, right? But I think it's also about strategy. So I think right now their main business is elsewhere. But I think as soon as we see, management level decisions and, to focus on these emerging markets more, I think there is like lots of room for even more momentum. But of course, it's understandable if you just look at a business model of a company, they're coming from a different angle and have also other challenges and, and trying to keep market share in what they're known for and what they're commercializing now. But it's great to see how they're putting also, their eggs into different baskets, right? Ion, superconducting. I think they have a sensing department as well. So
basically at around your master's, so you had exposure to 2D materials, you had like the measurements there were transport measurements, meaning like lock-ins.
Yeah, I think it was another example or I think it often happens in a master and a PhD, that you are stuck in the clean room or fabricating for so long that the measurement, part is much shorter than expected. But yes, it's just a DC transport characterization with lock-ins, like you said. But luckily, I got to pick these type of measurements up in my PhD as well.
Exactly, because then from there you, I guess you started looking for PhDs, and you chose Copenhagen, Niels Bohr Institute, and Charlie Marcus, which I mean, it's it's not a bad choice given that it's probably one of the top 5 places in Europe, easily, for quantum transport and quantum computing and so on. How did you choose them? Did you apply many places or?
So I think if I remember and look back, for me it was, I was in Germany for a long time, but I had this drive to, explore, go abroad. I did a small project in Durham in England during my bachelor as well. And I started, traveling as much as I can. And then for me, it was clear, no, I need to, do my PhD elsewhere. And that's why I started looking around. But for me, it was also clear it should be in Europe, right? I didn't want to move for 3 to 5 years. Some natural candidates for me. I had a friend already who started a PhD in Paris. So I found Paris very interesting, London, and Copenhagen was on my radar because my master group, they had a small collaboration with Charlie in Copenhagen already, and we got some material from them. So I think this is how I first became aware of the group. And I think at that time I was not even aware that this is, a world leading group in, transport measurements, Gatemons qubits, Majorana physics, and that they're so tied to like Microsoft. And I think it was funny. I just, sent Charlie my CV and he invited me to present, my master's project and work. So I flew over, gave a talk, got to meet the entire institute, and it was just amazing for me, coming from this smaller university group. First of all, I came on a beautiful summer day to Copenhagen. Everybody was biking, so I think I fell in love with the city right away. But then, this research environment in Copenhagen is very unique. Charlie, tore down all of the walls. It's a super open lab space where the different groups were collaborating, and it was such an amazing atmosphere overall. I got to talk to all of the students, really hung out with them for a few days, and got to ask my questions, how they like it. And I felt, I think for me, it was clear then, this is the place where I want to do my PhD. And then it was up to them, right? I had to wait for a few weeks until I heard back if I got the spot or not. But it seems like the feeling was mutual. So I was very excited that I then got to go to Copenhagen.
And did the topic play any role in this choice at all? Or, because this was like a transition now from the classical into the quantum.
Mm-hmm. So I worked already a little bit. So these 2D materials and carbon nanotubes I worked on, there was a theory proposal from the Regensburg group that you could realize some Majorana bound states in these systems. So, and I think that's why also I thought I'd come to Copenhagen and will work on these types of physics. But it was also very nice. Typically, when you join Charlie's group, the first few months you would just look around maybe at first, what is everybody doing? Where do you fit in? So you don't have to know from the first second on what you're going to work on. And it's typically like that, right? Because you should explore, and you don't just have one project. Typically you have many as well. But then I arrived and there was a PhD student, Albert, and he at the time needed more help on his project. So he sort of grabbed me and he's like, yeah, you're joining basically the small Gatemon team here. And I'm very happy about this because I really enjoyed working and getting to know the circuit QED. So circuit QED was very new to me at this point. And yeah. But I think I'm happy that it was just a happy accident again. I feel I was not as strategic back in the day. I think this changed a little bit. But there I was just very open. I think in general, I tried to be very open-minded and see, just feel into me is this bringing me joy? Do I find this exciting? And try to go down that path. And that worked out well so far.
Yeah, I've of course met Albert because he was for a while in ML4Q and came to Cologne. So this is where we met. We actually lived only about a 5-minute walk away from each other here in Cologne. So it was that's pretty cool. And of course, Charlie Marcus is technically my PhD grandfather. So there's, it's a small world. The lab in Copenhagen is amazing. I've also visited, we had the Delft Copenhagen collaboration. Probably I visited in 2017, or I can't really, place it anymore, but I thought the lab was, like Marcus' lab is very tightly run, you feel, right? Like there's probably, they put a label on the label maker.
Yes. Yeah. Very true. No, it's like, it's always clean. I think it's just some things they teach you as well, right? And I think it is important. And now whenever I go, I mean, I see a lot of different labs, and, you know, I've seen very chaotic labs, and, you know, but then of course, when you're exposed to the Charlie lab for a few years, like this is your standard. And then you're trying to, but it also, of course, if you have lots of visits and in general, it just makes things easier, right? I think it's just, showing respect to the lab as well.
Yeah, no,
and,
but I totally can understand that if you were there as a master student and you saw this lab, I think it's a very cool place, and it's very easy to be productive if you have a well-organized lab.
Yes. And I think, in general, you know, Denmark is also like known for that. They're very structured. They think things through. Education is, of course, a big theme and in the center. Then having Charlie come in and also, you know, bring this immense research expertise and expertise of building labs. I mean, he's like known for this, that he did it at multiple places, right?
Yeah, exactly. I mean, he now moved back to Washington. It's just like he has been at least Stanford, Harvard,
Copenhagen, and then Microsoft as well, right? So.
No, and I also really liked, I always felt it was quite interesting when you come into the lab there. It's a little bit cramped, like the rooms with the fridges are very close to each other, like all the experiments, everything is rather close, but it's tidy and you can work there. And it feels like a place where you can, where there's proper work, lots of cables, Like I think if somebody comes there, it really looks chaotic, but it's very, because of all the cables and all the,
I saw some PhD students, you know, typically you have to go through that. Your setup is chaotic. And then, you know, once a year, it's like, no, we're doing a full cleanup, and you're trying to debug and make it new again. Especially for the large scale experiments. I think it becomes, you know, a huge chaos if you're having, you know, tens of lines. I think nowadays it gets easier, right? But back in the day, you had mixer components, amplifiers, you had so much, you know, individual components somehow connected at room temperature. Yeah. But this, of course, now also moves either into the fridge or into the control system. So you really just have the cables between the electronics and the fridge themselves. So I feel, we're making big progress there as well to have the entire setup simplified for these experiments.
Yeah, already a shout out to your current employer, Quantum Machines. And I don't know if it's Quantum Machines or already QDevil, but for example, like back in my day and still in our lab, when you want to measure a different Hall bar or a different nanowire, you have to put the cables into the respective on the respective slots in the breakout box. But there's now these breakout boxes where you can wire automatic, like that you can reroute in the computer, which is amazing.
Yes, I think you're referring to the Q switch, right?
Exactly, the Q switch.
Yeah.
And you probably didn't have a Q switch during your PhD yet.
No,
right?
No, just the standard breakout box and standing there and switching.
So indeed, I think that the Q switch is naturally something that will clean up the labs, because you don't have to disconnect it again. You just connect your transport measurement and then you
and it's nice, right? I think many students, want to measure while they're on the move, at home on the weekends. And then back in the day, you might have to come in and flip the switch, but now you don't have to do that anymore because your setup is entirely electronic, like controlled via software.
Did you enjoy the frustrating cleanroom work?
Yeah. So I think it's, in general, when you start, it's like, it's a ramp up, There's so many tools, and I think they were quite structured. Also, how Albert taught me all of these. It's great that there was already a structured approach, and we didn't try to do all of the tools in just a few weeks, right? It's like first you do these two tools. So, and then yes, it was frustrating at times. I still remember, I think this was actually, something very, heartbreaking. We made this Gatemon device, Albert and me, and then, I was still like learning. So it was really, we wanted to make a hero device. And then at the last stage, going through, like each of these chips went through 10 lithography steps, which is anyway, getting it to the finish line was already, amazing, because you also have wet edges in between, and then often the edge fails. But then we had it in the saw, right? Because we had, I think, 4 devices on like a larger wafer. And then somehow the water the chip was not like stuck properly on this tape for the saw, and when the water came, it just flushed away the chip. And I think Albert was hunting also for this chip in the machine, and we could not find it. And this is like, these are the very frustrating, heartbreaking moments, when you're already invested not just a week, but often, 2 weeks or longer in just a single fab round, and everything looks great, but then in the very last moment, it sort of breaks. Yes, and I think I also had, of course, I did a lot of dry etching then for the stencil project. And there it was also painful, dry etching and fine tuning and working there with systems who also, need maintenance and are not as reliable because maybe you're using a recipe, but you're tweaking the parameters and you don't know how it comes out. So many, many hours, but overall I enjoyed it. I think, during my PhD, I also, when you are in these moments, I think I said to myself, this is normal for a PhD student. Everybody has to suffer before there is, light at the end of the tunnel. Yeah.
A friend of mine once told me that when he enters the lab, he feels like it's playtime. He enjoys it as much as,
Yeah. No, I always felt I learned something as well, right? And it's nice when of course, first I had a project with Albert and more people, like there were also postdocs involved and other research assistants. But the stencil project was then something I decided to jump on, because Morten Kiergaard came back to Copenhagen. He did a long postdoc at MIT. He also did his PhD back in the day with Charlie. And then Andras Jenisch, who did an assistant professorship. And they had these themes of, they were interested in the stencil topics. And I was like, oh, I'll jump on this. This sounds like exciting. I'll spend more time in the clean room and check this out. I don't want to do Gatemons anymore. It's
Yeah, I mean, we can maybe briefly say, indeed, the Gatemon is sort of a hybrid of a superconducting qubit and a quantum dot device, like a semiconductor superconductor hybrid. And they are cool, like they have interesting properties, but they're also very, very frustrating for the people who work on them, because the yield on these devices has been much, much poorer than standard superconducting qubits.
Exactly. So if you look at Josephson junctions and how they're like realized, typically you have an aluminum oxide junction, right, where you just need to oxidize the aluminum lead. But with these semiconductor junction devices, I mean, there are multiple ways on how to realize them, and each has its intricacy, right? You couldn't just take BLS nanowires, wires that grow in a chaotic manner on a chip, and then you need to transfer them onto your substrate chip. And we try to use 3-5 layers, so something that is selectively grown, but then you need to etch many layers away again, because for your CQED circuit, you want to be on a silicon, you want to have a silicon surface. And yeah, so it's a lot of material physics at play, lots of different types of fabrication processes that you use as well, that then have, influence on the performance of this chip. And like you said, the yield is very low overall. We were happy that, some of the chips went to the finish line, but maybe it was a yield of 5%, right?
And what's really cool about it is that you learn to measure transmon qubits, which is good because that's very related to some of this, like in principle, quantum machines came out of superconducting qubit control. But you also learned it on bad qubits. And to be honest, it's harder to measure a bad qubit than to measure a good qubit.
It's very painful. And I think back in the day, I was also using systems that were making it very painful. So now when I measure with quantum machines, right, I measure typically at the IQCC via the cloud, and it's like unbelievable. I can just go there, and then these are okay qubits. They're not, insane, but I can just go there and run, an RB sequence or a 2-qubit gate. And this was like me a few years ago that would have been on these qubits, like impossible.
Yeah. I'm a co-author on one of the papers on early Gatemon stuff. And, it's more tricky. And I mean, you also have to bring out an oscilloscope. Like, let's say if you measure a qubit that has a 20 microsecond coherence time, then, you can just put a bit more spacing between your pulses and you're fine. But I guess if your time is like, if you have 100 nanoseconds, you really want to make your pulses short. You have to make sure they don't overlap. So you have to be very precise.
Exactly. I think I was also deep in this land of, overlapping and non-overlapping spectroscopy, like things you typically don't think about. But if you have this very low coherence, you need to come up with other tricks on how you can actually measure these systems. And so I appreciate that I had a hard time, because typically that is what teaches you and educates you on these systems, and I think makes you appreciative on how far we're actually come. So I'm constantly like in awe of what everybody's doing on these, with these systems, because I know, I've seen the other end, or like the beginnings from it. So
yeah, just a brief thing about the stencil lithography. So the idea there on the project is to make superconducting qubits, but not with resist, but with this hard mask based on like silicon oxide, silicon nitride materials like this, right?
So I think this was like the themes that were out there. Typically when people make stencil masks, they are based on silicon oxide or silicon nitride is very popular here. But so I had actually another postdoc and another PhD student jumping on my project. Like once I started, after a few months, they got very interested as well in it. And they worked on MBE growth. And I think that's why they got very excited, because how can you make actual devices fully in situ, right? And their stencil masks are the only option, because you cannot put any organic resist in these machines. It needs to be clean. And then we also saw, using these silicon nitride stencils, they are extremely thin. And so if you think about superconducting qubits, one of the issues we have there when you do make your shadow evaporations is that you always have these parasitic layers, right? And this comes really from depositing from two angles. And then it was actually so easy to think, what happens if we have a thick stencil mask instead of just a very thin one? Because when you have a thick one, then you might start blocking some of the deposition depending on which angle it came from. And making it thick, silicon nitride is not a good material here, but silicon itself seems to be the candidate. And they're also on that front, they're actually commercially available silicon membranes in that thickness. And that's how I started working on this platform instead of, making these silicon nitride masks myself. And then the problem just became, deep etching a thicker mask.
And beyond just writing papers, you also got into writing patents during your PhD, right? Mm-hmm. So how different is it to write a patent or a paper?
Mm-hmm. So I have to say that at the Copenhagen University, and also with Charlie and Morten, they had like a great team and assistance on how to get this done. So for me, I think, and my colleagues, it was just more of a manner of, making a nice, presentation, writing down in Word these concepts and novelties. And then, if you look at patents, it's very, the language is legalese, nothing that I'm familiar with or good at. But we had these tech transfer office, and they assigned a person. And so we had a lot of meetings with that person, and they helped us, really transferring the language from like the physics and the findings to this, patent language. And so I'm very happy that I was just able to utilize a process that was established, because of course, Charlie, Morton and co, they already published other patents as well during their time there. And so I was like able just to utilize a process that they established. And yeah, so I think I don't remember it as, a hard task or anything. It was really just breaking down the concept and having clear graphics and schematics on it as well. And then making the patent, attorney, making them understand these concepts so they can formulate it in a way how it goes into to the official documents.
So from PhD, did you decide to move on into the quantum industry immediately? And what was your thought process behind that?
So I wanted to move to industry. I think this was very clear for me also in the last PhD year, also maybe with the patent process, there was these themes of, so KU has an entrepreneurial program where they actually push these technologies, not to do it. But these themes for me were there, industry, startups, more business related topics. And then I had a colleague, Fabio Anzaloni and Jost, who are now colleagues at Quantum Machines. And they asked if I'm interested in doing an industrial postdoc with Quantum Machines and QDevil. So this was very typical. And because both of them were actually also in industrial postdocs before they, rolled over into their current role at Quantum Machines. And they thought, okay, I'm already part of this ecosystem. And they think, I would be a great fit. And the idea was actually to work on quantum interconnects. So still very experimental. But long story short, I joined the company, but started working on different things. Not on this project. So I got dragged in further into the product team from early on. And again, I think I was at this point, I knew I wanted to go more into the industry, wanted to maybe stay in Copenhagen, but it was not really clear yet what I want to do. It's, I was very busy with wrapping up my PhD and thesis, and I actually didn't want to make a decision, but then this decision, fell into the same time. But then I think in hindsight, I was like very happy how it worked out, because I really got the exposure and the role that I wanted and that I didn't even know existed at this time, right? I think a part of me was afraid that I would lose lose touch with research and, state of the art. But it's the opposite is the case. I think I was never more engaged in, being aware what's going on, especially on the superconducting qubit platform and all across the board, not just fabrication, but quantum error correction, control, or how we solve other problems inside the fridge, for instance. So, yeah. Mm-hmm.
How did you find the transition from an academic setting into a company culture?
Mm-hmm. So I think what I noticed at first was the words that everybody used were different. There's lots of different business slang. There's much structure, many more meetings. But I found the transition, I think, okay. I took something to heart that our people manager basically said in one of the first meetings. They said to be very proactive, and I tried to be as proactive as I could. And that made the transition, extremely easy for me, because I met a lot of people. First of all, I felt extremely connected in a very short time frame to everybody around me. And I was very excited by what we're doing in overall. And one thing I was very surprised by, which I didn't expect, but of course, with a PhD, you have expertise in a certain field, but I still felt, very young, entering the industry field. But then I had colleagues who were, older and more experienced in other fields that looked at me as an expert, in superconducting qubits. And I was like, what do you mean? It was like a new feeling to me, but of course we have many experts from different angles, and then together we're building these products and driving our roadmap forward. But yeah, but I really wanted this transition, and I really thrived then in this transition. So it was easy actually after a few weeks and months to leave the academic me sort of behind.
I mean, but indeed, like this company thing, it is quite lucky. Like you were in Marcus' lab, and let's say QDevil, which is now part of Quantum Machines, was a sort of a spin out of the Niels Bohr Institute, right? So the company was very connected with the institute.
Exactly. And I think that's made it easy. I knew basically some colleagues that I now have were postdocs at the Niels Bohr Institute as well. So I think having that made it also easy, right? Not everything was new and unfamiliar. I had already people I knew from before, that made it extremely, amazing to start out just because it was not completely detached. And then I was still working, actually. I had an office at the Niels Bohr Institute for only this year I moved, right? But I was once a week working from the university. So because the connection to the labs there is just still very strong.
And I'm a big fan of your products. I mean, for example, here in Andolab in Cologne, we do use the QDevil PCBs. And I mean, it is like there's so much that is changing, and this professionalization of the field is also helping basic research, because like not everybody has to design a PCB for, gigahertz access and make sure that you don't have magnetic components and all this stuff.
It depends what your goal is, right? I think some students, electrical engineers, I think it's very valuable when you learn also how to make a PCB, especially because these are often, experts that then also go to companies like Google and whatnot. And we need experts that learn this. But if your goal or your project has its focus elsewhere, then of course you're wasting time. And then it's much smarter to use something that has been tested, right? And is, suitable for the experiment that you want to do.
Yeah, exactly. So I think it's very nice because I mean, I have looked into this type of design things a little bit. I mean, basically whenever you design something like a PCB, it always takes longer than you want it to take. And, I mean, it's even worse with electronics. So indeed, like quantum machines in some sense acquired, a platform to put in chips and like the packaging and so on part when they, acquired QDevil. But, the quantum machine side of things is really in the control stack, right? So let's talk a bit, about quantum machines and sort of their core business and your role.
Yes. So I think quantum machines really sits at the heart of quantum control and quantum control for scaling up, right? For really achieving fault tolerance at scale with a variety of, qubit systems. Yes, we're coming from the superconducting qubit side because one of our co-founders built, the first version of the OPX. So this is our flagship product back in the day when he was a postdoc at Yale. And he also identified that, what is out there is not sufficient for the quantum error correction experiment that I want to do. And I think at the heart of this is that I think people forget that you want to do quantum processing, quantum control. A big part of it, or almost the entire part of it, is classical, right? How do you generate the signal? How do you acquire it and process it? And then what do you do with this processed data, right? And I think we're seeing that. I think it's captured in this term adaptive control, that is because, back in the day, or how we used to measure a qubit system was very static, right? You have a waveform sequence, you play it, you acquire signals, and then you just, analyze the signals, but it's not really a back and forth or like a real-time interaction. And quantum machines, really identified that this tight connection between quantum and classical is essential for measuring and operating quantum systems. And this is like the foundational philosophy that is driving everything that we do today. And that's why we also, for instance, collaborate with NVIDIA, because we're constantly, thinking about what is really required for quantum computing at scale, and especially from the embedding of classical compute side, and how do we make it accessible and bring it as close to the qubit as possible, right? It could be on the cloud, it could be on your computer, but then you have millisecond communication streams, and you don't, if we look at the coherence times, of course we're losing here, right? Because our superconducting qubits or spin qubits are not on millisecond, lifetimes. So we really need low latency control, and feedback cycles. And this is, what we're focusing on, and accelerating basically and changing how we actually controlling quantum systems.
And what is your role in the company as a product solutions physicist? Is it talking to customers but also to investors?
So, I'm part of the product team. So, right, there is like a bigger technology branch within our company that develops our current products and our future products, and that works very closely with R&D. But then we'll, of course, also work very close with sales and marketing. So my role is sort of dual-fold. On one hand, I help, with all of the technical discussions that we have with customers or with future customers. So it's about really, they have an experiment, they have a challenge and a problem, and I need to understand this and then show them how we solve this with our products that we have. So often it's really understanding how is their setup, what configuration do they need. And often these are new experiments that they want to do, right? So then it's about bringing this knowledge in and then making sure that we understand what features are needed in the future and help drive our future roadmap. So it's this dual fold, it's towards the customers, but then also internally making sure that we make use of this knowledge and gather it in a meaningful manner and get it immediately into our roadmap so we can iterate, much faster on the solutions that are required. And as you know, if you look at quantum computing, there are many problems across the entire stack. And the faster we can iterate and, build products, the faster we will, reach all of these milestones. And some of the companies have very ambitious goals, and we are here to meet them. And we need to be ahead of time as well, right? If they want 10,000 qubits, in 2030 or 2028, we basically need to be ready with the system, 1 or 2 years before that.
Let's say, your company has the superconducting qubit genes, let's say. Meaning you're building fast control based on FPGAs, using microwave frequencies or like baseband pulses, and like generally would have pulses with time resolution in the fraction of a nanosecond, and like that's all. That's all coming from this side. But there's many. Funny enough, many qubits are sort of microwave qubits, right? And V-centers have microwave control. But for example, optical readout. So then the challenge becomes, I have my microwave control pulses. I guess that you guys can do immediately. You just put your box there, but you need to integrate it with this optical readout, for example. Is that?
Exactly. This is what we're doing. I think we're just not as known for it yet because we have this, probably this picture in the community as well, that we're very much focused on superconducting and spin. But like you said, NV centers, we have, especially in Germany, we have a lot of labs and companies working with our hardware. And it's either they can use the microwaves directly, or of course you can use our system to trigger other instruments and, also connected to the optical readout components and still utilize these fast feedback and the processing. It's just a matter of how you then integrate the system with your existing stack.
And of course, let's say the most impressive platform of the last, let's say 3 years or something is the neutral atoms, right? And there you have this massive feedback problem of taking these camera high resolution images of the big neutral atom clouds with the lattice of Chord atoms, and then you have to act on this and do feedback. So I guess you guys are also in the business of trying to understand how to connect this camera images and do feedback based on them.
Definitely. I think in general, neutral atoms, it's a very exciting field at the moment. And their challenges are on a completely different end, right? Also, how to really have this optical tweezer control. And then, like you said, on the readout is so slow. So can we help with our technology to, first of all, make it faster and connect it to the processing and feedback power? But yeah, we have experts internally coming from many different platforms. So, it would be very exciting to see how we progress in this avenue. Mm-hmm.
I think this is super exciting. I mean, the basic piece of technology is this field programmable gate array, right? Like, which is sort of a programmable. It's not really you program the gates, so it's a very, very fast computer. It can do relatively basic computation. How would you describe it?
Yeah. So I think an FPGA, it can do very advanced things. You can even run neural networks, but then it's this level of how you do it. Because if you need to be an FPGA programmer to unlock these, functionalities, you might spend years of just, programming a single thing.
The FPGA is a very basic, form of computer, but indeed it's not, it's not as easy to program an FPGA as it is to program a regular computer.
Yeah, so I think that's why you also have differences in, all of the other players that try to build FPGA-based control. But I always see it like this. It's a canvas, and then you program the functionality into this canvas. And if you have very sophisticated programmers, who then also build sort of like an abstraction layer, that gives you intuitive access to this chip. That is how we unlock, novel and easy intuitive programming for many types of quantum systems. And this is what we did. So the chip actually has a lot of advanced functionalities, but you don't have to do FPGA programming. You actually use a language that looks like Python. So I have a math library. I can, calculate sine. I can even run small neural networks, but I utilize sort of like the power and functionality that I have in Python without having to think about these FPGA intricacies. And this is something we got like extremely well done. So, we have play and measure pulses, if, while, for loops. So, your standard package that you get. And now you can use it for quantum without having to be an FPGA programmer or worry about this very advanced classical computational element. Mm-hmm.
And FPGAs, they are not usually running as high a clock speed as, let's say, a CPU. Mm. So the FPGAs that I work with are maybe somewhere between 200 and 500 megahertz probably. But quantum machines uses sort of the top of the line FPGAs on the market, right? That's like, let's say there's many companies there's Q-Blocks, there's Zurich,
Instruments,
Zurich Instruments, Q-Blocks, and so on. You have a bunch of companies, but you are really the ones that use the sort of most top of the line FPGAs. That's maybe a fair way to put it.
Yes, I think it's of course the FPGA, but then really, I think it's about what you do with the FPGA and how you integrate it in your entire, system architecture, because that is like one part, but then you also have an digital to analog and, a DAC and an ADC path and components there. So it's of course FPGA is one component and how you program it, but then also how you integrate it in a wider, architecture that, provides excellent, signal quality. but then doesn't come at the cost of, logic. So we really focus on having this embedded compute combined with excellent analog performance. And typically what I see out there is either you need to compromise on one of them, but for quantum computing at scale, you need both. So we're, very focused on, especially when scaling up, that both actually improve and work hand in hand.
Yeah, maybe we can just quickly try to give people a sense of the problem. So let's say you have a 200 qubit quantum computer or something like that, which is measured every 1 microsecond or so. And the measurement is somewhat analog information, like will be digitized. Like, let's say the measurement pulse is 300 nanoseconds, and every point in these 300, it's probably comes out to be half a nanosecond points or something. So you have 600 points every, with, 8-bit or something precision every 1 microsecond, which produces a lot of data. And all of this data needs to make decisions on the lifetime of these qubits while they are still alive. So you need to have you need to process this data, which I guess quickly becomes, megabyte or whatever level data. And you need to make decisions in, microseconds, or that's sort of
exactly in nanoseconds, actually, right? Depending on the classical operations that you do on it, that takes a few clock cycles. But then you want to be as fast, right? As soon as the processing is done, you don't want to have microseconds. You actually just want a few tens of nanoseconds until your next pulse operates. And you want it to happen without having to recompile a program, right? You want it to be within a program and have this sort of like logic built in that it can do decision making on the fly.
Exactly, because we should say that in principle, your lab computer communicates with these FPGAs and, for example, uploads waveforms or, programs and so on. But these uploads, they take, I'm going to say, millisecond level time, or they are not exactly. This communication is slow, or at least it's like even if the upload is fast, the latency is
exactly
relevant.
It's Ethernet cable between your PC and the control electronics. So that's why you're typically in the millisecond scale. And that's why for large scale like quantum computing, you don't want to upload waveforms. You actually only want to upload instructions and programs, like you said. And this is what you can only do with an FPGA based program, right? It interprets, it executes on instructions that you give it, which is great, because I can just say, have this Gaussian, pulse shape, and then stretch it, or have like thousands of them, and you're not limited by any memory here, because it will, play it as an instruction and shoots out the waveforms accordingly.
And exactly, and I think this is something that's sometimes underappreciated, like in the public. Indeed, like this classical compute behind quantum computing is pushing boundaries, and let's say you have this FPGA, which is a very high level product already, and it's connected to a coprocessor. Like there's some Linux running computer that is directly connected to the FPGA on the same chip, right? And that then communicates via Ethernet with the lab computer. And you possibly have multiple FPGAs in your setup, so you need to think how they talk to each other, right? So
exactly. Actually, the amazing thing is, if we have one chassis and it has 8 modules, each module has an FPGA. So if you think about 200 qubits, there is a lot of processing power behind. But the great thing is that we also have all-to-all connectivity. So what we do is we program each of these individual FPGAs. We call them so-called cores, similar to the classical core. And then you have 16 cores per FPGA, and those can talk to any other core or FPGA in the entire large-scale system. So you really get all-to-all channel connectivity, meaning if I do an operation or have a processing result on qubit 1, I could play in ultra-low latency a conditional pulse on qubit 200. Although it's coming from a completely different, channel that sits on a different module and chassis. Yeah. So we thought a lot about the architecture and connecting everything with each other, because this is required, right? If you look at quantum error correction specifically and running these large scale circuits, those, how we execute those, of course, motivate and guide our system architecture.
Yeah, from the perspective of a theorist, the FPGA looks like a universe in itself.
It does, right?
Yeah, and just a quick question about NVIDIA, because this is, of course, very interesting. Like the FPGA, there's already, the FPGA is one thing, but there's always the question whether at some point people will move to ASICs, right? Like specifically designed circuit. The FPGA has a degree of flexibility, but if you really want to do the same thing every time, you can also just hard build it into your silicon.
Completely agree, yeah.
And NVIDIA, of course, has GPUs which can process these large amounts of data very quickly. So are you guys thinking of how to connect GPUs to FPGAs? Is that the
we
name
did
of the
that.
game?
Yeah, we did that actually already. So with NVIDIA, we have a deep collaboration, and we launched a new product already called NVIDIA DGX Quantum, where we connected now our OPX system with the FPGAs to their Grace Hopper super chip. So it's a CPU GPU super chip. And now those two can communicate in under 3 microsecond latency as well, which is phenomenal, because now you have this, very powerful classical server that can do, even more than what you can do on the FPGA. For instance, if we think about decoding, I think decoding, it's a classical algorithm. We will have to have many decoders probably running in parallel, especially for large scale circuits. And so this architecture, of course, allows you now really to do real time, error correction, not just error detection, because I think this is what, some companies and labs showed, but it's about real time error correction, because keeping track is one thing, but then actively, deciding what to do next. And for non-Clifford gates, I think it's essential to be able to do mid-circuit, measurements and operations and feed forwards. And this capability of having, first of all, very fast loops between the QPU, the FPGA, and then the GPU, comes in. And then, of course, decoding on GPUs, I think it's also an open question. What is the system? Do we have ASICs, another FPGA, CPU, or GPU? And there it is still very open, because depending on what kind of quantum error correction code you're going with, the platform you're working on, there might be different, classical components that are better suited for the problem that you have. And for us, it's just important that we're working basically with all of them. But we're already seeing now that I think especially for LDPC codes, GPU seem to be a great, platform to do that.
And just to put in one it's like the microsecond latencies, they are a lot for superconducting qubits, but not a showstopper, because in principle you can have fast feedback decisions like, qubit reset and things like that on one level, and then these bigger syndrome corrections every 10 microseconds or something, and it would still be fine. But to be honest, of course, this GPU connection for ion traps or for Rydberg atoms, which have a bit longer coherence times, it's maybe already good enough for many of their applications.
But it's actually also good enough for superconducting qubits. We did Quantum Machines, I think, did work led by Yaniv Kurman on the control requirements. So before we even went into this collaboration and built the system, we looked at what are the requirements, and we looked at superconducting qubits. There were actually an application that was guiding deriving these control requirements, and it was running Shor's algorithm. Shor's algorithm on superconducting qubits and factorizing the number 21. Yeah, and we've simulated because you need more than 1,000 physical qubits for this. So basically from this experiment or from this application, he simulated it and we derived what the decoding, latencies need to be, this laid the foundation for us setting where, setting these system architecture boundaries. And the great thing is, we did this. And now if we look out there, what, Riverlane and IQM and so on, think about this, they also, we're converging to the same numbers. So it seems having these latency links, on the lower microsecond scale is fine. And then for the decoding itself, between 10 and 20 microseconds seem fine as well, because you can have some lag, right?
Yeah.
It just isn't, you just need to make sure it doesn't get too big so everything, breaks down. But there is some buffer that you can have also for superconducting qubits. And assuming we are in the hundreds of microseconds, hopefully with coherence times, it should be fine.
Yeah, that's amazing. And that shows how hard it is to do business development in this space, because you are developing a business in a space that is not yet fully mapped out and that is very dynamic and exciting.
I think that makes it very exciting. I think you asked about my role, right? As a physicist, I find this extremely exciting because it's really thinking about the physics here, right? You're very, I look at the Google papers and the IBM papers, the AWS, just see and trying to understand how they solve or trying to solve these challenges that we have. And then I get to think about the architecture that is needed to build the systems that they will need in a few years, because they have, crazy ideas and thoughts, and then we need to evolve accordingly. And I really like, being in this very dynamic space. You never know, maybe tomorrow another paper comes, across your table and you need to rethink your entire vision again.
Is this something that pushed you towards being a quantum content creator?
It's an interesting question. It's something, in general, I always have this nature of just testing things, and then they seem to evolve into something bigger. And I think it was the same with this content creation or writing. I like writing in general a lot, and I think I just wanted to have an outlet for it. And I'm very surprised still how well it is received. But also notice that now that I have this industry angle and I talk to a lot of different stakeholders, that I can bring this value of communicating to a wider range of audience. And, that makes me also very happy, and it seems to make others very happy. And I think that's why it's like the self-fulfilling loop where I just continue doing it.
And you have posts on LinkedIn, you have a newsletter, and I guess you also get direct feedback from people, which is probably on the one hand rewarding, but it's also really good to be challenged, I guess, right?
Yes, yeah. I think I'm also testing myself, sometimes, how offensive or can you be with, your writing style, or how is this, received? And often, you put something out and you would expect a certain, feedback, but then it might be completely different. So it's very interesting for me just to see as well how the community thinks about topics. And I'm often still surprised. But I see it as an experimental physicist, right? For me, it's an experiment as well. And the newsletter, I think I asked the audience, do you want to have something like that? And they're like, yes. And I was like, oh, I did not expect this. Okay, here I am writing a newsletter.
But so how is it in your job? I guess you have exposure to different types of quantum architectures and platforms. Mm-hmm. So you already this exploration of trying to better understand them is sort of really synergetic with your work.
Yeah, it's, of course, I'm still very much focused on superconducting qubits, but I'm very interested in the other platforms as well. And there are often synergies, right? For instance, I think with the stencil work, I worked with a PhD student at DTU in Copenhagen who worked on silicon photonics. And I found it very interesting that he utilized the dry etching techniques that I did for my stencil work for silicon photonics. So I feel there are often many similar themes, and I really enjoy, jumping on all of these different ones. And then this is also what sort of like brings value in, because I hear or listen to something, I can categorize it and can immediately also inform my colleague about it. So I think it's also getting this information in and being able to forward it to whoever, might need this information, or I could contribute to like their work. I think I like this a lot. So it's extremely synergetic in that sense.
Yeah. I mean, the field is evolving really, really quickly. And my way to keep on top of things is by reading your newsletter. But how do you stay on top of such a rapidly evolving field?
I think talking to customers, I think this is probably something that comes with this job, which has, makes it very natural to stay on top of what's happening. And then on top of that, it's also a little bit of a behind the scenes view, right? That you typically don't get because it's often just, projects that PIs or, companies talk about doing, but there is no paper out yet. So I think this, of course, is like a big advantage of working at a company like Quantum Machines, that you naturally get this sort of like exposure of what is happening. And then I'm also, LinkedIn, I think, became the place for, the quantum computing community. I'm not so active on other channels, but yeah. And then archive, I think this is something I cannot shake off, right? This is like the academic part. And I think I still enjoy that like the most, just having a coffee and browsing through archive and seeing what's new here.
Is it that some people now already come to you with, hey, we have this really cool piece of news. Do you want to talk about this? Are you now at the level of fame where people come to you, or?
A little bit, but not about papers, actually. It's more on the commercial side, I would say, where people would appreciate, some more help with, their branding or like their technical communication. This is like a very, that's very interesting. And I think it's very exciting that this is happening. I think students are a bit more humble, they're happy. They're super excited when their work gets picked up. So I got a lot of, nice messages from them. Being very appreciative if I picked up, papers from younger PhD students, for instance.
And how do you see the other, like the overall quantum like space of creators of communication? I mean, IBM is amazing. Like they have probably done the most thorough community building in the quantum space, right? But then there's people like Sabine Hossenfelder, who's very controversial, but still has a lot of probably a lot of reach, right?
For sure. I think she has a few million followers, or at least 1 million, if I'm not wrong. I think I first thought of, I don't know why I thought this, but in the early stages when I got into the LinkedIn writing, I thought, oh, the space is saturated, because I also saw IBM and, them putting out either blog posts, writing on LinkedIn or YouTube videos, right? I think they're one of the only ones who really focus on their Qiskit channel. And then I think blog posts in general are more common, but also not as pushed, I think, by the community. And now that I'm, more active, I realize how big of a gap it is, but also that more trying to fill it, right? And I feel also companies and startups are keen on filling these gaps. So I think it's just a matter of time that we will see many more people being more active in this space. But it's very early, and it also takes a lot of, dedication and discipline. So I do this not as my main job, right? And I think, but with AI and other tools, I hope we're seeing good content and not too much, because I don't like the AI generated content. I think I'm seeing way too much. But I also trust our algorithms get a bit better and help with the filtering out here.
I think for Chris and I also, this is not our main job. We have, I've just completed my PhD and he's still a postdoc, but we really enjoy doing this. And I think that's what makes us also keep wanting to do it more.
I think
Yeah.
it's amazing. So first of all, I really appreciate being on and having this chat with you. Uh, so I think for you also, you get to meet so many different people, right? And I mean, probably you personally also, I consume podcasts a lot too. I think this is just a new medium that emerged in, the past few years. More and more. And this is how people learn, right? Educate themselves. It's much more nicer than watching a lecture and somebody, of course, these are great things too, having really a lecture, but often I get much more value just from listen to, a story of someone, like how they see the philosophy of their company, their technology. So this format, I think, is like great. And so it's awesome that you want to continue doing it. I think fantastic work and yeah, don't stop it.
No. And I think indeed, like this quantum field, like it is something that needs to be very connected. It's still like, I would say that we now see much more bridges between, with the FPGAs and so on. It's really a technology that now bridges several of the main quantum, platforms. So there will be more connection between NV centers, ion traps, Rydberg atoms and superconducting qubits. They all sort of have a similar overall control problem.
Yeah, they all need classical, compute, right?
Yeah.
And I think probably it's just a matter of, it is also natural. If you look at how a lot of the students and engineers learn measuring on these systems, it's still very, if you're coming from an academic lab, you might have not used these systems yet, right? So of course, it's also it was a process for me to understand these systems. And because I came from working on an AWG and having to debug for a month first before I could measure, right? So I think, but I completely agree here with you. We will see many more of these themes, also much more discussions between the communities, because often problems are similar, and there's lots of technology transfer that can happen and that will happen, so that all of these technologies can progress.
But what is maybe your field, maybe big picture quantum industry? We are currently at a very, very exciting time, but we are also in a very difficult time because the economic situation between the US and Europe is becoming difficult. China will build a lot of this technology, the DIL fridges, but also this control stack on their own because they are already behind, let's say, export restrictions, I suppose. So the overall quantum market is in a very, there's a lot of excitement, but there's also a lot of turmoil. Like, how do you see it?
Yeah, I think it's with any kind of technology, I think, that is, emerging and that could bring huge economical advantage to countries, right? Or not just economical, it's also military, right? I think that's why many of these technologies are already having these export controls on them. I think we're just not used to it yet, but if we look at other technology that emerged in the past decade, I read a very good book on the semiconductor chip war. I think if you get a bigger picture on the history and the politics of that technology, it's crazy. And I think similar things will now happen with quantum computing, of course, because every country tries to, get there first. And because we also have this AI.
Indeed, the pace is unusual. And we have this AI explosion at the same time, which is really, how much will the AI explosion change FPGA programming? Is there like let's say writing VHDL or similar languages, these hardware languages of FPGAs is kind of tricky. Will LLMs be able to learn it and do better than humans?
So I assume so, but I think what I want to mention here is that, of course, our software and logic team, I think they have these tools like Cursor integrated in their daily workflows already. So I assume they can iterate already much faster. And even for me, I mean, I'm not using it for FPGA programming, but I'm very surprised how I can, code up new experiments and then run it and basically simulate it and get the sequence. So I think half a year ago this didn't work, and now using Cloak Code it works, and I'm very surprised that maybe I only need one iteration of an error and it fixes the error immediately. Because I think a year ago or so, you still had all of these iteration, and maybe sometimes it worked for, smaller examples, but it just gets smarter and smarter. So, I think just how we access and develop, and, everybody will sort of like be a product manager and product developer. You can have many more different roles that you have in a job, because you have these tools that you can use.
Yeah, it's super scary. For example, I write GDS files for our cleanroom work, and we write them using Python, of course. Like there's some programmatic way of drawing a layout for a chip. And I was using an old Python library, and I wanted to switch to a newer Python library. And of course, I can now just take my old code and, tell Visual Studio Code Copilot to a GitHub Copilot to just translate from this library, like do the same sort of stuff in another Python library, and it does it. And I think if you did this, as a human I did this with find and replace, it would take me forever. It's like 3 days of horrible work, but it completely will change the job of an experimental physicist. Like we are already writing our scripts. I don't know.
Yes, it changes the work of an experimental physicist for sure, of like any student, right? I think also how they approach now learning and teaching. And then it, of course, affects every role in industry. It doesn't matter if you're in a technical role or in a business role.
I mean, we're getting to the end, but I wanted to ask you a fresh question of LinkedIn, which is quite funny, from Alan Ho, who's also very active. Anybody in the quantum space will have probably seen him post, and he posted this question: what will the terminal valuation of quantum hardware companies that succeeds to build commercially useful quantum computer at scale be? And he says, well, greater than 5 trillion, 1 trillion, 500 billion, 100 billion, or less. What is your feeling? Is it?
Yeah, I voted for it, and I sat in front of the question, and I'm like, oh God, how do you even judge this, right?
Yeah.
Because I also recently followed a little bit more about the predictions that people have on NVIDIA. And I think what Wall Street says and what NVIDIA says or AMD says, there's like a big gap. Because on one hand, you could see a huge explosion that you really have, 2-digit growth every year, and you reach these trillions. For quantum, I think I would be a bit more moderate still, because we are in such an early stage. So I would not talk of trillions here yet. And I think that's why I put myself comfortably in the middle with 5 billion.
500.
500, sorry. Yeah, 500 billion. I think it also has a lot to do with the applications that we unlock and what they then unlock, and what who the end user there then is. There are so many stages that are like unclear how it will evolve. What do you think?
I couldn't. I think I even put 100 billion, because I'm always on the sort of skeptical side. I'm sort of thinking quantum computing will be very valuable for certain projects and for certain products, but I sometimes struggle to see that it would have as much impact as, let's say, AI in solving sort of everyday problems that people need solved all the time. So I would think that it's more of a specialized compute for certain problems, and that it can be very valuable. And also this intelligence angle, like the Shor's algorithm, that's nothing you can really earn money with. Well, you can, but it's like very government contract. This like.
And it's more like defense related, right?
Defense,
yeah. So it's not something that is for broader society and has, no, and also it will, I think what you also said, maybe AI captures it as well, right? You don't know how they merge and how do you then differentiate the value that is, created by one or the other.
I mean, for all of us, it's humbling, right? Like we look at all of this as physicists, and it's great that it drives scientific progress. But I don't know. Like, I mean, thinking about $500 billion is it's just a crazy thing to think about.
But the supply chain, I think, a big part is also the supply chain in there. And then what you really, provide in this whole value chain. So I think maybe most of this 500 billion might also just come from the ancillary ecosystem,
Yes. And I think indeed, like the technological push that quantum machines and many other companies in this space do might have other side effects that we can't even predict yet.
Yeah. Mm-hmm.
Completely. I think I watched an interview with Pete Chatball from PsiQuantum, and then he was asked as well, were there any interesting side effects that came out that you work on these, manufacturable, photonics platforms? And now because, classical compute and the AI industry, they also have these interconnects, problems, or try to, they're very interested in photonics at the moment as well. So it seems they're developing technology for quantum computing, but as a side effect, they might open up a huge market for classical computing. And I see this with quantum often because Josephson junction can also be used as transistors. IMEC is working on this, right? So you might have all of these additional, classical technologies that somehow are quantum, but because we need to refine the technique so much for the quantum processors, we get these amazing applications in other fields as well. So I guess we will see more of that, and I think that's great. And if you capture this under maybe then the 500 billion are realistic.
Yeah. The field is progressing really fast, but we can't say still much about it. So it's like, for example, when you first had computers, you could not imagine anything like AI. Yeah.
Exactly. Yeah. I like this. I think it was a recent paper from John Preskill as well, where they showed an iceberg. And then we only see the tip right now with applications, and there might be a lot hidden. And I think that makes me always very positive, especially comparing it to, the classical, IC world.
Yeah. Maybe to finish up, Quantum Machines is a growing company, right? So we have probably many PhD students and postdocs listening. Should they apply for jobs? Is there still?
Yes. So I think we're hiring aggressively. We're scaling a lot because we just closed the Series C earlier this year and have a big funding boost. So every department is currently basically hiring, especially our customer success physicists who go to the customer, bring up our system and work with them on experiments as well. So especially, experimental physicists with background on a specific qubit platform, I think they have great opportunities right now to, join our company in Europe, but also globally. I think we're hiring in the US and in Asia. So often we have PhD students, right, all across the world in Europe. So if you want to go back to your home country, I think there is a good chance that we're hiring there as well. So please reach out and join us.
Yes. Perfect. Then, thanks a lot for coming on the podcast, and let's meet soon at some quantum conference, I guess.
Yes, exactly. I'm not sure if you're making it to Boston in a few weeks. I guess it's too short notice. But I'm sure I'll come to Germany probably also much more often. Thanks so much. This was super fun.